afternoon to everyone. Today I am going to tell about the topic called cartesian product and a binary relation, which is taken from the MSCF subject. First topic is a Cartesian product. First of all, we are going to know about what is Cartesian product and how it will be. The definition of the Cartesian product is sometimes we want a collection of order pairs. Order pairs means collection of order pairs means like 1 and 2, which contain in a set like 1 and 2 and 1 and 3, 2 and 1, 2 and 2, which are in a set. So like we are the let's say we are interested in finding all the combinations of x and y coordinates where x and y the value should be not exceed then 3. So let us consider a graph which is x coordinate x and y axis. It contains values 1, 2 and 3. 1, 2, 3. So here we are considering the order pairs like 1 and 2, 2 and 1. The set of these two which is not exceeding the 3 value. Here a comma b for any a and b is called an order pair. We are considering a and b for any a and b is called an order pair. Here we have to note that when two values of a two values of a order pairs which are not equal, here note that a comma b and b comma a are not equal. Therefore, in an order pair does not matter. Next one is definition of a Cartesian product. Let's say when a and b are two sets, the Cartesian product of a and b can be denoted by a or b. If you take an example, another Cartesian products like let's C is one set and D is one set. The Cartesian product of these two sets are, which is represented as C multiplication of D. In the set of all order pairs a comma b, where a belongs to a and b. A and b, here we are considering a rule method a into b, which means the Cartesian product of a and b is set of a comma b, a belongs to a and b belongs to b, which means the a elements belongs to a and b belongs to b. The multiplication of the symbol is used to represent the Cartesian product a into b, and like that b into a, b comma a and b belongs to b, as a belongs to a, which is that's it. The Cartesian product of two sets we are representing here b into a and a into b. Note that any two sets like a into b, here this considering these two sets, note that a into b not is equal to b into a. Here we have to know that the Cartesian product of a into b, which is not equal to b into a. The Cartesian product is also called as a cross product or a product set of a. Here Cartesian product, which is also called as a cross product. Cross product means multiplication like that, which is used to multiply the set 1 elements with the set 2 elements of with each element of set 2. That is known as a cross product. Let us take an example 1. What is the Cartesian product of a? A equal to 1 comma 2 and b is equal to a b c comma. Here we are given two sets. One is a, one is b. One is a and one is b. Let us do a Cartesian product for these two sets. Here the solution is Cartesian product of a into b is first multiplying the 1 with the element a, 2 with the element b, 1 with the element a and 1 with the element b, and 1 with element C. Here we are doing first Cartesian product by here given A into B. So first the elements, each element of A which is multiplied with done the cross product with each element of B, like 1 into A, B, C. After 1 we have to consider 2 into 2 cross product of A, B, C. So here we have to remember that A cross product of B, which is not equal to B cross product of A. So another example, if A is equal to 1 comma 2 and B is equal to 3 comma 4, here we are verifying whether this given node A into B, which is not equal to B into A. Here we are taken example A comma B. So cross product of A comma B are 1 comma 3 and 1 comma 4 and 2 comma 3 and 2 comma 4. So cross product of B comma A is 3 comma 1 and 4 comma 2. 3 comma 1 and 3 comma 2 and 4 comma 1 and 4 comma 2. So here we for every here we are verifying that the cross product of A and B, which is not equal to B and A. So now note 2 is, for any two non-empty sets A and B, if there is an n element in A and m elements in B, then the number of order pairs in A into B will be n into m. So whether we are here we are knowing that the number of order pairs for a given particular cross product. So here given here we are taken an example for A, set A and set B, like set A contain A and B and set B contain P, Q, R. So if you want to know the number of order pairs in the cross product of A and B, by not doing the cross product, we will also find the order pairs, the number of order pairs. So this is the formula, n into A into B. So to then number of elements in this A and into the number of elements in B. So 2 into 3 is equal to 6. So here note 3, the null set cross product of A is equal to the A into null set is equal to null set. From this definition, we knowing that null set cross product of null set and A, which is equal to set of A comma B, and A belongs to null set and B belongs to A. There is no such pair A comma B where A belongs to and B belongs to A. Similarly, A cross product of null set is equal to null set. Therefore, A null set cross product of A or cross product A into cross product null set is equal to null set. So next we are going into the binary relations. Here the definition of a binary relation is that let set A and B are two sets. A binary set relation R from A and A to B is a subset of A comma B. Here R, if there is any two sets, a binary relation if there is a binary relation from A to B is a subset of A cross product of B. Here we represent that as binary relation is a subset of A into B. Here we are recording A cross B is a set of A and B, A belongs to B. Generally we use the notation A is a relation on B. A is a relation to denote the A comma B or belongs to the relation. Example, let we consider a two sets A comma B, which contains A contains element 1 2 3 and B contains 0 1 2 4. The cross product of these elements, these sets are given 1 0. This is like, let's say R is the relation where a comma b belongs to R. If only if a is equal to b, then R is equal to, if there is any relation a comma b, if there are any two sets belongs to the relation when they are two equal, when a equal to b, when both a and b equal, then they are belongs to the relation, are considered like this. The graphical is here we are seeing the graphical representation of order pairs. Here arrows are used to represent the order pairs of a relation. Here is the relation on these order pairs 1 comma 1 1 2 comma 2. Here we are going to the next topic, types of relations. First one is reflexive relation. A relation on a set A is called reflexive if a comma a belongs to R. For every element a belongs to a. In other words, for all a comma a belongs to R. If here R is a relation on set A, is called a reflexive when a comma a belongs to R, when a comma a belongs to the relations of R, where a belongs to a. In these words, for all a or a comma a belongs to R, let's take an example. For a set A contains 1 2 3 4. First relation is first is contain the 1 comma 1 1 comma 2 2 comma 2 2 comma 3 3 comma 3 4 comma 4. Here the relation R is reflexive because it contains all order pairs from the all order pairs from the a comma a. For every element of a belongs to a, R has 1 comma 1 here a set. For every a elements, it contain the a all order pairs like 1 and 1, 2 and 2, 3 and 3, 4 and 4. It is called the reflexive relation when it contains the every element of a, like relation a comma a. It is known as reflexive relation. Here we will take another example. R1 is equal to 1 comma 1 1 comma 2 2 comma 1 2 comma 2 3 comma 1 4. Here we are not this is not a reflexive because here there is 1 comma 1 2 comma 2 4 comma 4, but there is not 3 comma 3. So that's why we are not considering it as a reflexive relation. So the next one is irreflexive relation. Irreflexive relation is a relation on a set. A relation R on a set A is called a reflexive if for all a belongs to a comma a not belongs to R. Here taking an example. Here one example, a set contain 1 2 3 4. Here R3 a relation is equal to 1 comma 2 2 comma 1 3 comma 3 4 comma 4. It is not reflexive because 3 comma 3 and 4 comma 4 is there in R3. Here 3 comma 3 and 4 comma 4 are belongs to R3. Here we are saying that a comma a not belongs to the relation. Here the relation contain the 3 comma 3 and 4 comma 4, so it is not considered as a reflexive relation. The next we are taking another example. R4 1 comma 2 and 2 comma. It is reflexive because it does not contain the elements like a and a comma a because 1 comma 1 2 comma 2 which belongs to the reflexive relation. Here irreflexive means which not contain the order pairs like a comma a which is not equal to which is not belongs to the set R4. Another one is a symmetric relation. Here the definition of a symmetric relation is considered as a relation R on a set A is called symmetric if b comma a belongs to R holds when a comma b belongs to R. For all a belongs to b comma a and b comma for all b belongs to a. In other words, relation on R a set A is a symmetric if a and b belongs to the a comma b and a comma b belongs to R and b comma b belongs to R. Here symmetric relation means it should contain the set of elements like b comma a and a comma b, where for all a comma b belongs to the both same set A. Here taking an example, 1 comma 1, 1 comma 2, 2 comma 1, 2 2 comma 2. Here it is symmetric because for every element a comma b is contained b comma a, like 1 comma 2 and 2 comma 1 in R5. So there is no need to check for 1 comma 1 and 1 comma 2 because it contains a comma b, b comma a, like 1 comma 2 and 2 comma 1. Here asymmetric relation means a relation R on a set A is called asymmetric if for all A and for all B, A comma B belongs to R, B comma A belongs to R, which is A is equal to B. Here we have another note point that in asymmetric relation, when both wherever we have A comma B in R, there will be a B comma A until or unless A equal to B. Here we have to consider that the A element should be equal to B to consider as a antisymmetric relation. For example, we are taking a relation 1 comma 1, 2 comma 2. Here A comma B, B comma A. Here A is considered as 1 and B is considered as 1. In this A is considered as 2 and B is considered as 1. So here on a set asymmetric because 2 1 is in R7 but 1 2 is not in R7. It is a antisymmetric because 2 1 is in R7 but 1 2 is not in R7. The next transitive relation means for a relation R on a set A is called transitive when for all A, for all B, for all C, which is set contains A comma B belongs to a relation and B comma C contains to relation, which there should be present A comma C. Here we are taking an example of set A 1 2 3 4 and relation is taken 2 comma 1 3 comma 1 3 comma 2 4 comma 4 is, which is transitive because we are verifying that here it should contain A comma B and B comma C and A comma C. If these conditions are true, we call it as a transitive relation. So these relation is called a transitive because it contains 3 comma 1 and 2 comma 1 and 3 comma 1. Here A comma B and B comma C. Here A comma C is present. Here A3 is considered as A, 2 is considered as B, and 2 is considered as B, 1 is considered as C. Here A comma C present, therefore RA in RA. So it calls it another example 2 comma 1 and 1 comma 3. It is not transitive because there is 2 comma 1 and 1 comma 3. A comma B and B comma C. There should be comma B and B A and there should be a set called 2 comma 3. Here the 2 comma 3 set is not present, but that's why it is not a transitive relation. And next one is asymmetric relation. A relation on a set A is called because for all A and for all B and A comma belongs to R and B comma belongs to R. Example A is equal to 1 2 3 4. Here we are considering a relation 1 comma 1 and 1 comma 2 1 comma 3. This is not asymmetric relation because of 1 comma 1 because here A comma B belongs to R, B comma A not belongs to this relation. Here 1 comma 2 is present which is not 1 comma 1 because of 1 comma 1 this is not called as a asymmetric relation. Here we got 1 comma 2 and 1 comma 3 2 comma. It is an asymmetric relation is A comma B and here there is no B comma A, so it is called as a asymmetric relation. Here we are summary for every property which we have discussed until now. First relations like reflexive, iterative, which is binary relations, a type of relations, and that we are discussed in these that are relative, reflexive, symmetric and antisymmetric and the asymmetric and transitive symmetric. So for the respective relation there should be a respective property which we have to consider to show that the relation is true. So that's it. Thank you.